This steel block remains stationary because the tension in these cables pulls with equal strength in opposite directions. To maintain this stillness, the forces acting on the object must cancel each other out. In mechanics, we define this state as equilibrium, the condition where the net external force acting on a particle is exactly zero. Newton's first law dictates that equilibrium applies to a particle at rest, but it also defines a particle moving in a straight line at a constant speed. In both cases, the sum of all external forces is zero. Consider the simplest case of equilibrium: two concurrent forces acting on a single point in space. For this particle to remain in equilibrium, the two forces must have the same magnitude but perfectly opposite directions. We express this through equation 4.10. The negative sign indicates the directional offset, allowing them to sum to zero. Because these opposing vectors cancel out, the particle experiences no net external force and remains in its current state of motion. However, maintaining this balance becomes more complex when a third force interferes. Real-world structures like suspension bridges rely on these principles. At any connection point, multiple cables exert tension, yet the node stays fixed because forces balance. When three concurrent forces act on a single particle, equation 4.11 states that their vector sum must equal zero for the particle to remain in equilibrium. This means the combined effect, or the resultant, of any two forces must be equal in magnitude and perfectly opposite in direction to the third force. We can visualize this balance by rearranging the vectors. Placing these three concurrent forces in a head-to-tail sequence, they form a closed tridobal. The final vector ending exactly where the first began provides geometric proof the net force is zero. If the vectors form this closed shape, the particle cannot accelerate. The geometry proves that no leftover force remains to change the particle's velocity. This logic scales to any number of forces. Whether there are 4, 6, or dozens of forces acting on a single point, the requirement for equilibrium is the same. For any number of forces in equilibrium, the head-to-tail arrangement will always result in a closed polygon. The physical closing of the polygon confirms that the mathematical sum of every force acting on that point is zero. If the polygon is broken and the shape fails to close, the gap represents a net external force. In that case, the particle is no longer in equilibrium and will begin to accelerate. The rule of polygons allows us to see equilibrium as a geometric shape, but to solve specific engineering problems, we must use an algebraic approach. In the laboratory, we use an analytical grid to break these complex angled forces into their component parts. We treat these diagonal vectors as a combination of horizontal and vertical shadows. By applying a coordinate system, we can deconstruct a difficult two-dimensional problem into two independent one-dimensional calculations. This diagonal vector resolves into components by projecting onto the axes, giving an x component and y component. By equation 4.12, equilibrium requires the sum of all x components and y components to equal zero. In a three-dimensional system, we apply this same rule to the z-axis. All three directional sums must cancel out to ensure total equilibrium. Take a 6-kilogram mass suspended by a rope and pulled sideways by a 50-Newton force. We resolve the rope's tension into its parts. The vertical component must exactly match the weight of the mass, while the horizontal component must cancel the 50-Newton pull. Equilibrium is the result of perfect cancellation. By breaking forces into their components, we can reduce even the most complex mechanical systems to a series of equations that sum to zero.